Hello everyone. Today we'll be presenting our project on a custom splint design for carpal tunnel syndrome. This is by Elizabeth Crawshaw and Nathan Archambeau. Carpal tunnel syndrome, or CTS, occurs when pressure is placed on the median nerve in the wrist. This compression leads to common symptoms such as numbness in the hand and fingers, tingling or pins and needle sensation, pain, and weakness in the hand. CTS approximately affects 3.8% of the U.S. population, making it a widespread condition that can significantly impact quality of life and workplace productivity. It is commonly associated with repetitive motions, poor ergonomics, and prolonged computer or tool use, and is recognized by OSHA as a work-related musculoskeletal disorder. As engineering students, this is especially relevant due to the amount of time spent on computers and in hands-on work environments. This past January, I was diagnosed with carpal tunnel syndrome in both of my wrists. My doctor recommended that I wear wrist braces at night to keep my wrist in a neutral position and reduce symptoms. The black braces shown here are what I was prescribed. While they do provide support, they are bulky and uncomfortable, which makes it difficult to sleep. As a result, poor sleep began to impact my daily performance and ability to complete schoolwork. At the same time, I wanted to avoid invasive surgical options, especially at a young age. The pink gloves shown are another common option, but because they rely on compression, they can actually worsen symptoms by increasing pressure on the median nerve. To better understand the current marketplace, we looked into what an effective carpal tunnel brace should provide, and I also tested several of these braces myself. One of the main issues is that comfortable braces often lack sufficient structural support, while more supportive options tend to be too stiff, bulky, and restrictive. Additionally, limited sizing options, typically small, medium, and large, can lead to a poor and uncomfortable fit. Velcro straps are another drawback, as they can be inconvenient and uncomfortable. Personally, I've had them catch on blankets during sleep, which can be frustrating and disruptive. Finally, despite medical recommendations, very few braces extend past the wrist, which limits their overall effectiveness. These images show examples of braces currently available on the market. Starting on the left, this brace appears comfortable, but it does not provide sufficient structural support and does not extend far enough past the wrist. The next brace includes more support, but again it does not extend far enough to stabilize the wrist. In the center, this brace is specifically marketed for carpal tunnel syndrome. While it does provide support, it is bulky and restrictive, and includes a thumb splint that may not be necessary for all users. Finally, on the right, we have a compression glove. As mentioned earlier, these can actually worsen symptoms by increasing pressure on the median nerve rather than relieving it. Overall, these examples highlight the trade-offs in current designs between comfort, support, and usability. To address these challenges, we set out to design a brace that aligns with established treatment principles for carpal tunnel syndrome. First, effective relief requires maintaining the wrist in a neutral position, which helps reduce pressure on the median nerve. Nighttime splinting is a well-established, non-invasive method to achieve this. From a design perspective, we focused on improving overall effectiveness through proper fit, since braces, like cast, work best when they are tailored to the individual. We also aim to enhance comfort and usability by creating a custom, patient-specific design and eliminating the need for Velcro through a slip-on approach. Additionally, we extended the support past the wrist to better follow medical recommendations while ensuring the brace could be used primarily at night with the option for daytime wear as needed.
Next, we will move on to the design of our prototype. The prototype was modeled in Onshape. To model the contours of Elizabeth's hand and arm, 2 images were added to the studio and scaled using drawings on her arm, which were measured with calipers. Ellipses were created around each measured diameter. Using the spline tool, the outline of the arm and hand was traced on the top and right plane. A loft tool was used to create the shell. After designing the model in CAD, the brace was 3D printed with TPU. To lower print times, only the hand portion of the model was printed. 7 iterations were printed before printing our first full-scale prototype. Each iteration changed 1 or 2 aspects to fit the hand better. The first iteration had to be cut open to allow the hand to fit through, as it could not fit through the wrist hole. A slit on the side opposite to the thumb was added for the second iteration to allow the brace to open and fit the hand. The 4th iteration added a slot for a metal rod that was used to keep the 2 halves together. The 7th iteration added a cross link between the halves to prevent the sides from sliding up and down the metal rod. The metal rod seemed like a promising idea on a smaller scale, as it would close the brace and provide support for the wrist. This is the full design with the metal rod slot for support that incorporates all of the changes from the iterations previously presented. The metal rod used was a 6 by 100 mm stainless steel rod, which spanned the length from the bottom of the brace to the wrist. To print this design, the rod slot needed 3D printed supports. Since TPU has strong adhesion to itself, the supports were printed out of PLA using a multi-tool head printer, since PLA and TPU do not bond strongly to each other. However, after printing the first full-size prototype, we quickly realized this idea was not going to work. The rod was unable to close both halves of the brace, and it was difficult to remove the rod from the slot. Furthermore, it was bulky and strayed away from the objective of this brace, which is to be more comfortable than the currently available options. To improve this design, we decided to implement holes besides the slit where the two sides of the brace could be laced together, like you would see on shoes. This design is much simpler than the one with the rod, and it could be printed without supports, which decreased printing time by about 1.5 hours. Our final prototype is 3D printed out of TPU and uses elastic thread and a crisscross pattern to hold the halves together, as can be seen in the image on the left. The model was printed with one-layer walls and a gyroscopic infill to give the printed section a squishy, more comfortable feel. The brace is custom fit to Elizabeth's hand for a better fit and feel as compared to the ones available on the market. The TPU provides adequate support to the wrist without allowing it to fully flex in any direction. The model took about 3 hours to print and used approximately 38 grams of TPU filament. The length of elastic thread used to keep the halves together totaled approximately 1 yard. As for the cost of the brace, the filament cost is about 76 cents and the elastic thread is about $1.10, totaling $1.86 for the whole brace. To improve this brace, there are a few recommendations. First, the fit of the brace could be improved if the arm and hand were 3D scanned. A 3D scan would provide better contours than sketching from two images that are not perfectly to scale. Also, implementing a tongue under the laces, like one found on shoes, could prevent imprints and irritation from the elastic laces. Adding a fabric cover over the skin or around the 3D printed portion of the brace could improve comfort and reduce the risk of skin irritation. Using softer materials such as TPE or foaming filament could also improve comfort, as 95A TPU is still quite a hard plastic. If softer materials are used, a metal support embedded in the print could help stabilize the wrist. Finally, adding holes or removing areas where support is not necessary could also improve airflow to reduce discomfort from heat buildup. In conclusion, we were able to design and 3D print a custom brace based on the geometry of Elizabeth's hand and arm using scaled images. The brace meets our objective by providing a better fit and being more comfortable than the fabric braces currently found on the market. As for learnings, we learned how to design complex models using the spline tool and geometry from images, along with how to use the loft tool with guides. We also learned how to use TPU and PLA in combination on a multi-tool head 3D printer for easier support removal. Here are our references.